Hello, this is Jorge Rodriguez. I am the founder of Quality Analytics Advisors, LLC, your trusted partner in all operational excellence matters. What do? We offer training, certifications, and help companies with Lean Six Sigma reliability and other tools such as change management, predictive analytics, or simulations. Please visit us at lean6sigma.net, where you can find more information about us. The topic that I want to bring to you today is how to execute an analysis of variance, also known as ANOVA. The tool of choice for today will be Excel. In other videos, I'm going to show you how to actually do this in Minitab, in Python, RStudio, and you will see how easy it is actually to set it up. But if you have Excel, you can probably create your own Excel worksheet to execute this at your place of work without making any particular investment in one of those softwares. I wanted to spend a few moments just going over the concept of ANOVA and what it means. I welcome you to actually read about ANOVA. A good resource to actually learn more about ANOVA is to go to the NIST website and look into their statistical content. I think they do a pretty good job of explaining analysis of variance. First, analysis of variance is a statistical method that we use to determine if two or more means are significantly different. To do this, we need to formulate a statement that is known as the null hypothesis. In this statement, we're going to state that all of the means are equal. Remember, we have two or more groups. Sometimes in books, they call them treatments or populations. So we have two or more, and that's where ANOVA applies. And our null hypothesis is basically going to say that all of these means are equal. So in other words, ANOVA is a test of means. We need to formulate a counter argument to the null. We're going to call that the alternative hypothesis. In that counter argument, we're going to state that at least one mean is different from the others. To be able to execute this, we need data. We need to write a null hypothesis, and here's how we're going to write that. We need to write an alternative hypothesis, and the alternative hypothesis is that at least one mean is different. Not all, at least one that is different, the null hypothesis will be rendered ineffective. Then we have to declare what is the level of risk that we're willing to take in rejecting the null when it's actually true. We call that alpha. Alpha is also known as the type 1 error. For the most part, alpha is going to be set at 5%. That is customary to have an alpha of 5%, but you could set it at 1% or 10%. But the alpha level is going to drive your sample size. Higher alphas will require less sample. Lower alphas will require more samples. Then the ANOVA is basically going to calculate a p-value. The ANOVA methodology is going to end up by giving us a p-value that we're going to use to make a decision which way we want to go. whether we want to go with the null or whether we want to go with the alternative hypothesis. There are some key assumptions that we're going to make when it comes to ANOVA. The first is that the data is normally distributed. This means that the data follows a symmetrical distribution known as the normal distribution. The other assumption is that the variances for each of the treatments or each of the groups are equal. There's no difference in the variances. If the variances are different, there is a slightly different methodology called the Welch ANOVA. And we're not going to cover that in this content. The other one is that the observations are independent, that the data is measured on an interval or ratio scale, and that the minimum sample size is going to be 10 or greater per group. Some useful definitions. Anytime that we are solving hypothesis test type problems, we're going to be working with sampling distributions. One of the sampling distributions that we're going to use for the F is the F distribution. This is a statistical sampling distribution, very common in hypothesis testing. We can see it in ANOVA, which is exactly the tool we're going to cover today. And also is being used for tests of equal variances. To be able to use the F distribution, we need to calculate an F statistic. That F statistic is going to be a signal to noise ratio. The signal is basically the variance between the groups, and the noise is going to be the variance within the group. So the statistic tries to detect if there is a significant difference in the means, then the numerator will be bigger than the noise. And the F statistic will actually be a large number. If we get a large number, the image on the right will tell us that the p-value will most likely be small. Therefore, if the p-value is small, we're going to have to reject the null. So we need to know the significant level, alpha. We also need to know the F statistic, which we're going to calculate from our data. And based on that information, we're going to determine the p-value. One more thing, the F statistic is going to have something that we call degrees of freedom. We're going to show you as soon as I get to the ANOVA table what those are, but that's what is going to determine, and these are called the degrees of freedom of the numerator and the degrees of freedom of the denominator. These are called the parameters of the F distribution. That's what is going to tell us what is the shape of this curve that you have right here, okay? If the shape of that curve is different, that area will be different. Now, when it comes to analysis of variance, we need to calculate sources of variation. Those sources of variation are going to be represented by the total variation that exists in my data. We're going to call that SST. And we're going to break that total variation into two components. The variation that can be explained by the level of the factors plus the variation that cannot be explained by the level of the factor. We're going to call that the error. We're going to put that in a bucket that is going to be the red bucket here on the right. So how do we calculate these things? Here's the mathematical equation for this. Looks complicated, but you will see in a moment as soon as I go into Excel that it is not. The term on the left basically represents distances from each data point to the mean of all of my data. We're going to square that distance because it can be negative or positive, so we don't want to offset any contribution to the variance. That's why in statistics, we add variances, not standard deviations. That we're going to call the sum square total, and as you can see on my slide, it is a measure of the total variability observed in the data. Next, we're going to calculate how much variance is actually explained by the level of the factor or the treatment or the group that I'm using. In the example that I'm going to show you today, what we're going to be testing is basically if the distance that I get by striking a golf ball using 4 different driver designs is significantly different. So what we want to test is, does the treatment, in this case, design of the driver, has an influence on the distance? And if we can see that by calculating that the means are different, then we can state that the designs do have a difference in the means. So to be able to do that, what we need to do is to calculate how much the design contributes to the variation in distance. We need to calculate the sum square for the factor, and this is going to represent a measure of the variability due to the different levels of factor A. In other words, this is also known as between group variation. And then whatever cannot be explained by the factor needs to be noise. That is what we're going to call the error sum of squares. In other words, a measure of the variability due to the random process noise, also known as within group variation. Let's see this graphically. To calculate the sum of square total, what you're going to see me do in Excel in a few moments is basically take each data point and subtract the difference between that data point and the mean of all of my data, which I'm calling here the grand mean. I'm going to do that for each and every one of the tries that I did, or the strikes that I did with each of the designs. I'm going to square all of those distances and I'm going to add all of them up. That number is going to represent my sum square for my sum square total. Next, I need to determine how much of the variation it is actually explained by the designs. Remember, I have 4 designs of golf clubs: design 1, design 2, design 3, design 4. For each of these designs, I did several tests. And what I'm going to do next is to calculate what was the average distance for each of those designs. That's represented here by the blue line. Next, I'm going to calculate the distance between that grand mean and the mean for each of those groups. I'm going to square those distances, again, not to offset any contribution. And I'm going to multiply times the number of data points in each of the designs. I'm going to add those terms, and that's going to give me the sum of squares for the factor or the group or treatment, like some books call it. And then the last term is the amount of variation not explained by the factor. This can be easily calculated because I already know the sum of square total, and I already know the sum of square for the factor. Therefore, this is just a subtraction between those two. Graphically, we can see what it represents is the within group variation and from that particular group mean. The outcome of the ANOVA methodology is an ANOVA table. Once I execute the formulas, I'm going to put all of those calculations and summarize that information into a table that is designed to calculate the F statistic. I mentioned before that the F statistic is basically a signal to noise ratio. And that signal to noise ratio is going to be represented in this table by the mean square of the factor divided by the mean square of the error. So to calculate that, I need to calculate the sum of square for the factor, the sum of square for the error, and the total sum of squares. I also need to calculate the degrees of freedom. To calculate the degrees of freedom for the factor is going to be determined basically on how many factors I have. In my design, in my example, I have 4 designs of golf clubs. So A will be equal to 4. 4 minus 1 will be 3. You'll see it in a moment as soon as I get into the example. Then N is the total number of data points, and I'm going to subtract the total number of data points to the number of factors that I have, which is 4. That's going to tell me the degrees of freedom for the error. And those numbers are going to drive the term on the left of the F score. As you can see in the table, is the mean square, which is represented by the sum of square of the factor. I put my laser pointer here. So it's represented basically by this. So if I have this, I'm going to then divide by this, and this is going to give me this term right here. And if I have this, I'm going to divide this by this, and it's going to give me this term right here. Now, these degrees of freedom, the A minus 1 and N minus A, are basically going to give me the parameters of the F distribution that I need to use, where I'm going to calculate this p-value using this F score. We're going to see that in a moment. Now, depending on the value of this p value, we're going to either accept or reject the null hypothesis. Typically in statistics, we do not set accept. We say there is no evidence to reject. That would be more appropriate. When it comes to ANOVA, there is a roadmap that typically is followed. I mentioned at the very beginning that for this video, I'm going to consider the particular case where the variances are equal. But I do recommend that you follow this roadmap when executing ANOVA. First thing that you want to ensure is that the data is stable. We tend to say that a data set is stable when its variance and mean are not changing over time. Either the variance changes or the mean changes, then the data becomes unstable. Then I also mentioned that one of the assumptions in ANOVA is normality. So we want to verify through a probability plot or a normality test that the data follows the normal distribution. And the other step that we want to execute before running an ANOVA is the variances. If the variances are equal, then we can execute ANOVA, which is our example here today. We're going to see here that if the variances are equal, then we're going to execute the one-way ANOVA. To verify this, we can run something called the Bartlett's test for verification, or we can run a simple box plot or graphical analysis and see if the variances are significantly different graphically. If they look to be similar graphically, then you can run this. But if you have doubts, there's always the possibility of actually running a statistical test known as the Bartlett's test. There are other non-parametric tests that you can execute when the data is not normal, specifically the Levine test for that matter. So this is the scenario that we're going to be concerned with. Here's the example I've been talking about. A golfer wants to test 4 designs of drivers to see which driver on average hits the golf ball the farthest. He went to the driver range and tested each design 10 times and measure the travel distance in yards. We want to use ANOVA to determine if there is a difference in the average travel distance for any of these designs. So now that I have covered a little bit of the actual theory behind ANOVA, I want to show you that I went and verified these three things. A simple control chart can help me verify stability. And we can see that this data is very stable by design. A simple probability plot can help me verify normality. And we can say that the data by design is actually normal. It follows very nicely the different lines here. And we can see by looking at the confidence intervals for the variances of each of these designs that the variances are equal. And there's actually the result of my Bartlett test. You don't need to know this at the very moment. It's just to show you that I actually did follow the roadmap and I am dealing with data that meets these three criteria. So I can run the ANOVA test that I'm about to show you. Okay, so let's go to Excel and actually determine how to calculate my analysis of variance. So first, set up an Excel file like this. Your data can be stacked, meaning that you have design one and then below it, you're going to have this data. Or it can come to you like this, and then you're going to have to manipulate it to make it look like this. I particularly selected my data to sort of follow this design. So if I insert here in this particular design, if I go data, and I put a little filter here, you can see that I have 4 designs in this data set. Design 1, design 2, design 3, design 4. And here is my distance in yard. Here are all of my values. And there are 10. So there should be a total of 50 values here. All right, so first step, we need to calculate the sum square for the factor. We need to calculate this value right here. To do that, if you remember the content that I just showed you, we need to calculate the grand mean of this data. I'm going to put that value over here, grand mean. Basically, what I'm going to do is calculate the average by using the formulas that exist in Excel of all of my data. And that grand mean is 220.1. Next, I want to determine what is the difference that exists between this grand mean and this data point. So I'm going to calculate over here the difference between these two values. And I need to make sure that this value is actually fixed. So I'm going to put the dollar signs in between to this value so that it doesn't change as I scroll down. Okay? And make sure that we are squaring this difference, following the formula that I showed you before. So what we're going to do here is copy this, and then we're going to go all the way to the bottom here. Okay? All right. So that is my individual distances that I'm squaring from that grand mean. Then to calculate the total, the sum of square total, what I'm going to do is actually add all of these values. So I'm gonna sum, shift, control, arrow down. I'm gonna actually sum all of those values right there. And this is my sum of square total. Okay, nothing difficult so far. Again, to refresh, this is gonna represent the distance between this value and this value right here, and we're squaring those distances. And then all I do is just add all of them, and I'm gonna put that value right there. Next, I need to calculate the sum of square for the factor, which goes over here. So how do I do that? If you remember, I mentioned that for each of the designs, I need to calculate the mean. So I'm going to calculate the mean for design one. So I'm going to put here the mean for design one. And I'm going to leverage the data that I have on the previous slide. So I'm going to go to average. I can calculate a little bit more complicated formula in the data that I have, but I think it would be easier for me to actually do it from here. So this is the mean of design one. And I think this will work if I just do this. No, it actually didn't. So I'm going to calculate then the average for the mean of this design. And then here will be the average for the mean of this third design over here. And here will be the average for the mean of this fourth design that I have over here. So these are more my four group means. This is the mean of design one, the mean of design two, the mean of design three, and the mean of design four. As you can see, we are already noticing that these means are different. What we want to verify statistically is if these differences that I'm seeing are actually significant. And by significant, I mean that the p-value is going to be low. Each of these means actually have 10 data points. So if I go here, we can see that there are 10 data points for each of these means. So I'm going to fill that information over here. I'm going to put 10, 10, 10, and 10. And how many factors I have? I have 4 factors. All right. And then later I'm going to fill out this value over here, the R square. So I have 4 factors. And to calculate the sum of squares, what I need to do is develop a simple formula. It's going to be a little long, but it's basically going to be for the first value, I'm gonna multiply how many data points I have times the difference that exists between the grand mean and the mean of the design one. Remember that we're squaring this difference. Then I'm gonna add how many data points I have here times, and 10 is going to be a common factor, but I'm keeping it like this because you can have different values of n, and it is best to probably keep it like this at some point if you're setting this up for future reference. So in this side, what I want to do is then calculate the difference that exists between the second mean and my grand mean, and actually square this as well. Plus, the next one that I want to do is to calculate multiply times the difference between this and the grand mean, and I want to square that value. And the last number that I need to calculate here is going to be this. I'm sorry. We need to multiply by this first. And then we're going to do this minus this. And don't forget to square those differences. And that should give me the sum of squares. Now, it is actually a lot of error that is captured by the factor. Here we have the total variance, and this is almost 3,000, as you can see. So only about 660 something is not explained. That is going to be actually here. So we're going to do this minus this value. This is the actual way to do this. So we can determine very quickly the error in my ANOVA table. To continue filling our ANOVA table, the next thing that we need to do is to calculate the degrees of freedom for the factor. I told you that this is a minus 1, and a was how many factors I have, so is this number. So if we go here, we're going to say 4 minus 1. The error is going to be how many data points I have. So it's going to be the sum of this minus the number of factors. And then this is going to basically be the sum of these two, 39. Now, my mean square is going to be represented by this number divided by 3. And the denominator is going to be represented by this number divided by this. And we can see here that my F score is actually going to be very big, because F is basically going to be this divided by this. And my F is 53. This is a large F. If I go back to the PowerPoint and I look at the actual distribution, the F distribution, this is the value over here that this value is 53. And the shape is going to be determined by those degrees of freedom that I just calculated. 36 and 3. So 3 and 36. That's going to give me this shape. And this value is 53. I want to tell you that 53 is a very extreme value. It's actually very forward in this curve, meaning that this area is going to be very, very small. That area is going to represent the actual p-value, as you can see over here. In Excel, we can actually calculate the p-value. The way to calculate the p-value in Excel is by using the F distribution. The F distribution is here, and we need to tell it what is x. X is going to be this. The next thing we need to tell it, what is the degrees of freedom of the numerator, which is going to be this. And what are the degrees of freedom of the denominator, which is basically this. And then next, we need to tell it that this is the cumulative distribution. So we want to say true. And when we calculate this p-value is going to be the area to the right. So it's going to be 1 minus this value. So it's basically going to be 0. So my p-value is low. And if you remember, the way we constructed our null hypothesis here was that all driver means are equal, was our null. And our alternative hypothesis was that at least, probably should write this, all driver mean distance for all drivers are equal versus the alternative that at least one is different. Because our p-value is low right here, there is enough evidence to reject the null. So we have to go with the alternative. And I'm going to write here p-value low, H null, got to go. And we're going to keep the alternative for this particular scenario. So this is the one that we're going to keep here. The last thing I want to show you before I end the video is that from the ANOVA table, we can calculate a very important component. Basically, it's going to tell us how much variation is explained by the level of the factors. To calculate that, we're going to basically take the sum square of the factor and divide it by the total. And that's going to give me the R square, 81.5. This is going to represent how much variation is actually explained by the factor, and it's quite a lot. And that's one of the reasons why our p-value was actually low. So this is basically our content that I wanted to deliver to you today. I hope you have enjoyed this video, and I am committed to deliver more videos for you to fulfill one of the missions that we have at Quality Analytics Advisors LLC, which is to develop organizational capability in the use of statistical tools. With that, I hope to see you very soon. And I want to make sure that you subscribe. And for future certifications, please visit us at lean6sigma.net. Thank you. This was Jorge Rodriguez.